In this section, we discuss the difference between conservative and non-conservative forces. The gravitational force has the interesting property that, when an object is moved from one place to another, the work done by the gravitational force only depends on the starting and ending points of the motion and not on the path taken between the 2 points. For example, when the balls travel from heights h0 to hf, the work done depends only on the 2 heights and not on the path, even though in one case there was a horizontal displacement. For this reason, the gravitational force is called a conservative force. There are 2 different but equivalent ways to define a conservative force. The first one is as follows. A force is conservative when the work it does on a moving object is independent of the path between the object's initial and final positions. Another way to think about a conservative force is to consider an object that travels up and down hills and making turns, and finally ends back at the starting point. We call the path the object follows a closed path, such as in the case of the roller coaster when there are no frictional or air resistance forces present. In this case, h0 equals hf, and therefore no work has been done on the object. This leads us to the second way to define a conservative force. A force is conservative if it does no net work on an object moving around a closed path. A force is non-conservative if the work it does on an object moving between 2 points depends on the path taken between the 2 points. A classic example of a non-conservative force is the frictional force. When an object slides over a surface and kinetic friction is present, the frictional force points opposite the motion and does negative work the entire way. That means that the longer the path, the more work that is done by the frictional force. In this case, the longer the rough patch, the more work being done by the frictional force. In fact, if the object were to move back and forth over the rough area before proceeding to the right, more work would be done by the frictional force. In normal situations, conservative forces such as gravity and non-conservative forces such as friction or air resistance act simultaneously on an object. We can therefore write the total work done by the net external force as W equals Wc plus Wnc, where Wc is the work done by the conservative force and Wnc is the work done by the non-conservative force. According to the work-energy theorem, the total work done equals the change in kinetic energy, or Wc plus Wnc equals 1/2 mv final squared minus 1/2 mv0 squared. If the only conservative force is gravity, then Wc equals mgh0 minus mgh final, and mgh0 minus mgh final plus Wnc equals 1/2 mv final squared minus 1/2 mv0 squared. We can write this as Wnc equals kinetic energy final minus kinetic energy initial plus potential energy final minus potential energy initial, or the work done by the non-conservative force equals the change in kinetic energy plus the change in potential energy. Another important concept involves the potential energy. The potential energy associated with the gravitational force was mgh. And other conservative forces such as spring forces and electrical forces have potential energies associated with them. However, the concept of potential energy is not defined for a non-conservative force such as friction. In summary, we have defined the concept of conservative forces in 2 ways. First, a force is conservative when the work it does on a moving object is independent of the path between the object's initial and final positions. Second, a force is conservative if it does 0 net work on an object moving around a closed path. A force is non-conservative if the work it does on an object moving between 2 points depends on the path taken between the 2 points. Finally, the work done by a non-conservative force can be expressed as Wnc equals the change in kinetic energy plus the change in potential energy.